Hi, this is Juliette Shelton, and this is my Physics 2 Lab 4 on circuits and capacitors. So in this lab, we are using a circuit construction kit to measure currents and voltages in different circuits. And then at defined locations, we will use a voltmeter to look at the potential differences across the circuit and observe the behavior of resistors and capacitors. So a few fundamental principles we are using in this lab is first the conservation of energy. And so this is that the total electric charge in an isolated system never changes. And then we are also using the loop rule, which is the sum of the voltage differences across all circuit elements must be zero. And then the node rule, which is in an electrical circuit, the sum of the currents flowing into that junction is equal to the sum of the currents flowing out of that junction. So then for the RC circuits part of the lab, we are using 6 specified materials in series to explore the charge and discharge of a capacitor. We are using a 9-volt battery, a 10-ohm bulb, a 20-ohm bulb, a 30-ohm bulb, a 200 mF capacitor, and a voltmeter to determine the relationship between the voltage and the time in series. And then we are considering a circuit that contains only a charged capacitor and a resistor, and that is pictured below. So for the first part of this lab, we were presented a circuit with 2 batteries, each with 1.5 voltage and one 47 ohm resistor and one 100 ohm resistor. We were asked to find the current flowing through both ammeters. And then to do this, we have to use Ohm's law, which states that voltage is equal to current times resistance. So then after I plugged in the current and resistance values, I concluded that the currents flowing through I1 and I2 are both 0.0204 amps. And then we were asked to create a computer-based model for this circuit. I was able to confirm my predictions of the current values. Both ammeters read 0.02 amps. So when I replaced one of the ammeters with a voltmeter, the voltmeter read 3 voltage, which is the total voltage from the 2 batteries. And then the other ammeter read 0 amps. This is because the circuit is no longer complete and there was no current running through the circuit at that point. Then we were asked to find voltage readings across different segments of the circuit. I replaced the voltmeter with a wire to complete the circuit. And then for segment A, I found the voltage to be 3 volts. For segment B, I found the voltage to be 0 volts. For segment C, I found it to be negative 0.959 volts. For D, 0 volts. For E, negative 2.041 volts. And then for F, G, and H, all 0 volts. The sum of the voltage readings is 0, which means that the potential difference is also 0. For part 5 and 6, I removed the voltmeter from the circuit and then closed the circuit with a wire and used the voltmeter to measure the potential differences for each part of the path around the circuit and recorded the current I. And then the individual potential differences for a round trip around the circuit should sum to 0. And then the measured differences actually added to 0 volts, which is good. I used these voltage readings to construct a graph of the voltage along the circuit as seen here. Then for part 9, when I attached the voltmeter and altered the circuit, the ammeter reading did not change because its impact is negligible and will not cause any change in the amp reading. When I replaced the voltmeter with an ammeter in parallel with the 100 ohm resistor, the current read 0.06 amps instead of 0.02 amps. This was because the 100 ohm resistor is no longer in series with the ammeter as it was before. It is now in parallel with the ammeter. Now, because only the 47 ohm resistor is taken into account, the new current can be calculated by I equals VR equals 3 over 47 equals 0.06. And then lastly, I calculated the resistance of each of the following circuit elements shown below. In part 2 of this lab, we used batteries and light bulbs as resistors in order to charge capacitors. As the circuit ran, the 0.2F capacitor became charged. We used different resistances of bulbs, the first being 10 ohms. It took 9.95 seconds to charge and 11.25 seconds to discharge. And then for the 20 ohm bulb, it took 22.35 seconds to charge and 17.55 seconds to discharge. For the 10 ohm bulb, the current flowed counterclockwise for a few seconds until the capacitor was charged and the bulb stopped glowing. And then for the 20 ohm bulb, the current flowed in the opposite direction until the capacitor discharged and the bulb went out. Then for step 2, we had a 30 ohm bulb, a 200 mF capacitor, and a 9-volt battery. At first, discharging occurred rapidly, and then the rate of discharge decreased with time. Current flowed counterclockwise during discharge. In order to find the time dependence for this part of the lab, it was necessary to collect data on time and voltage. To do this, I started and stopped a timer and read the voltages at these times. I then plotted a time versus the natural log of voltage over initial voltage graph. This gave me the trend line of y is equal to negative 0.117x plus 0.0973. So then I was able to use the trend line that I found in the last slide to calculate the RC value, and I calculated that to be 6 seconds.